Hi, everybody. Happy Friday. This is March 27th. This is lecture 26. We're doing actually just one day on Stewart section 8.6, which is called Representing Functions by Power Series. So part one of the meeting is just an introduction to the idea of representing functions by power series. And it's mostly review, because really we've already done this. So recall geometric sequence, which is 1r r squared r to the n. So this is the formula an equals r to the n for n greater than or equal to 0. And the geometric series was this thing. Add up all those things. So 1 plus r squared plus r to the n plus keep going. And remember that that's a limit. We don't actually add up an infinite number of things. We add up a finite number of things, and then we add up some more, and then we add up more, and we see the pattern. And this converges. That is, this equals a real number. Only when absolute value of r is less than 1. So that means that r has to be between -1 and 1. Then we have the power series. Oh, sorry. When r is between -1 and 1, this series equals what? Anybody remember? Kinsey?
Is it 1 over 1 minus r?
No, you can't ask me. You got to tell me.
It's 1 over 1 minus r.
Good. Hey, well, now the corresponding power series we just replace those r's with x's. So we're going to have 1 plus x squared and this converges when absolute value of x is less than 1. That is, so the radius of convergence is 1. We denote it by capital R. And the interval of convergence. Anybody remember what the interval of convergence is? Marcy?
The interval on which the series is convergent.
All right, but what is it?
Yeah.
Including the endpoints? How do we figure it out? Let's just throw in some numbers. What if x was the number 1? Would this converge? 1 plus 1 plus 1 plus 1 plus 1? No. What if x was the number -1? 1 minus 1 plus 1 minus 1 plus 1? No. So the interval of convergence is just this. What does this converge to when it does converge? No. Give you a hint. It's staring you right in the board. Nope. Yeah, this is just this. All right. Now I want to introduce a function. What's the domain of that function? Want some new hands here. Looking at a function here. Notice that's a rational function. It's a ratio of polynomials. I'm only going to call on somebody who has not answered already. So let's get some hands up. So, for instance, when x is equal to 5, what's the y value? Negative 1/4. When x is equal to minus 3, what's the y value? 1/4. Good. When x is equal to 1, what's the y value? So, Ian, what's the? Yeah, so the domain is of the function f of x is all x's except negative 1. Now, well, yeah, if you're picky about your pluses and minus signs. All right. Now, but remember what we found over here is that when x is in this range, this equation is true. So when x is between negative 1 and 1, f of x can be represented by a power series. So f of x equals 1 over 1 minus x. And this is true when x is between negative 1 and 1. This is equal to 1 plus x squared plus that power series. So that's the series as n goes from 0 to infinity of x to the n. So I could use this formula to get f of 7. F of 7 would be 1 over 1 minus 7, so it would be 1 over minus 6, so it would be negative 1/6. But I can't use this series to get f of f of 7. So this formula, this function has a bigger domain than its power series representation. So I can use the power series to get y values only in certain cases. So that's an introduction to representing functions by power series. And again, we've already done it. When we found that this power series converges, we could think of it the other way. If I start with this function, for some x's, I can write that function as a power series. Meeting part 2 is basic examples. So basically, finding that result hidden. So recognizing that result, let me put this big star around this. this whole thing is result star. So recognizing star hidden in other problems. So lurking, it's really kind of sinister, lurking in other problems. So I'm going to do examples. Example 1. Find a power series representation and R and I. Remember what that means. That means the radius of convergence and the interval of convergence for the function f of x equals 2 over 3 minus x. Ian, what's the domain of this function?
Real numbers except for 3.
Yeah. So I start with a perfectly good function. It's good for all, this formula is good for all real numbers except x equals 3. Now, what I said is that we're going to be looking for result star, looking for this lurking in other problems. So here we go. We're going to rewrite f of x so that we can recognize star in there somewhere. So f of x is 2 over 3 minus x. So right away I can just pull out a 2 and write 2 times 1 over 3 minus x. But that's not quite what star says. Star says 1 over 1 minus x. So what can I do here? Well, let's factor out a 3. If I factor out a 3, then I have to put x over 3. So this is f of x is 2/3 times 1 over 1 minus x over 3. Now look, this is one of those babies. But with the thing inside not being just x, it's actually x over 3. But that's okay. I can just use result star, but instead of x's, put x's over 3. So this is 2/3 times the sum as n goes from 0 to infinity of, instead of x to the n, it's x over 3 to the n. Now, when is this valid? So what's the radius of convergence of this power series? I want some new hands in the air here. Silver?
Is it when it's between when x is between -3 and 3, not including the endpoint?
I'm not sure about the endpoints yet, but we certainly know we must have that the absolute value of x over 3 has to be less than 1. So that means that absolute value of x has to be less than 3. So as Silver said, that means that x has to be between -3 and 3. So that means the radius of convergence is 3. Now what about the interval of convergence? Now this would be 1 plus x over 3 plus x over 3 squared plus. So what would happen at the endpoints? What would happen when x was equal to 3? If x is equal to 3 in this series, what happens? Chase, you just raise your hand.
All the terms would become 1, and it's just 1 plus 1 plus 1.
diverges. What about when x is equal to -1? So, sorry, when x is equal to -3. So I'd have 1 plus -3/3 plus -3/3 squared. Chase? So does that converge? No. So the radius of convergence is that, and the interval of convergence is -3 to 3 without the endpoints. Now, our job, though, was to write the function as a power series. I haven't written it as a power series yet. So let's keep rewriting the function. So I can bring the 2 inside. And, well, so f of x equals 2 over 3 minus x, and that's equal to the sum as n goes from 0 to infinity. Bring the 2 inside. I'm going to separate the 3. It's going to be 3 to the n on the bottom, but there's another 3. So this is going to be 3 to the n plus 1. So there's my coefficients, and then my powers are going to be x to the n. And again, this function has domain all x not equal to -3, all not equal to 3. But this is only true when x is between -3 and 3. So you get a power series representation, but it's only good for a smaller batch of x values. So that's the first example where we recognize this result lurking inside of another problem. I'm going to leave star there for now, because I'm going to do another example. Let's find the power series representation and R and I. And R and I for this function. F of x equals x over 9 plus x squared. All right, somebody who has not answered anything today. What's the domain of the function I'm starting with? Annika.
All real numbers?
Yeah, the domain of f is all real numbers because the denominator will never be 0. Now, we have to get this into the form of star. So we're going to rewrite the function and looking to get star involved. So you can keep writing down your page. I'm going to come over here. F of x equals x over 9 plus x squared. So right away, I realize I want to pull that x out front. Okay, that's not quite star, though. Let's factor out a 9. So I can do that, factoring out a 9. Oh, and I can write that as x over 3 quantity squared. That's not quite star, though. Remember what star is. Star has 1 over 1 minus something. We don't have that. So we just have to force what we've got to go into that form. So you want a minus in the bottom, so let's put a minus in the bottom. So x over 9 times 1 over 1 minus. Okay, if I'm going to do that, I screwed things up, so I've got to put another minus sign in there. There we go. Now that's star. So this is x over 9 times the sum as n goes from 0 to infinity of that junk, minus x over 3 minus x over 3 squared. And all that's raised to the nth power. And this is only true when the absolute value of the thing inside, so minus x over 3 squared, that thing has to be, that value has to be less than 1. Okay, well the minus sign gets killed by the absolute value, so I just get that absolute value of x has to be less than 3 in the end. So that means that x has to be somewhere between minus 3 and 3. So this series is only valid for those x's, even though the original function is valid for all x. Now, we don't have this written as a power series yet. It's too messy. So, here we recognize star and we put in the series version of star. So let's bring, first of all, let's clean this up by writing the factors separately. So I have minus 1 to the n times x squared to the n over 3 squared to the n. And this is equal to x over 9 times the sum as n goes from 0 to infinity of minus 1 to the n. X squared to the n is x to the 2n. And on the bottom I have 3 squared to the n. That's just 9 to the n. Well, I still don't have this written as a power series. Power series is a sum of a bunch of numbers times powers of x. But I've got some junk out front. So let's bring that inside. I have minus 1 to the n. Now, instead of 9 to the n, I'm going to have 9 to the n plus 1. When I bring that 9 in from the outside, that means I've got one more factor of 9. And then when I bring in that power of x, I end up with x to the 2n plus 1. So our conclusion is that our function f of x, which is 1 over 9 plus x squared, can be written as a power series. Negative 1 to the n over 9 to the n, x to the 2n plus 1. But this is only valid for x between negative 3 and 3. So even though the original function has domain all real numbers, its power series representation does not. I didn't go through the details of checking out the endpoints, but I think you can imagine why this, when x is 3 or negative 3, this is going to diverge. So the interval of convergence is, well, the radius of convergence is r3, and the interval of convergence is minus 3 to 3 without the endpoints. So that's meeting part 2. Meeting part 3. Is differentiating and integrating power series. So there's an amazing theorem. It says this. What if you have a power series? So I've got a power series. Remember what that looks like. The sum as n goes from 0 to infinity of some constant times x minus a to the n. Now recognize that what we're looking at here is you can't really add up an infinite collection of things. This is the limit of partial sums. The partial sums are finite things. So there's a limit going on here. What if I park in front of this? The derivative of that thing. Well, the cool thing, the fact of the theorem, is that I can bring the derivative symbol inside. So recognize that the derivative is also a limiting process. Remember, the limit as h goes to 0 of f of a plus h minus f of a over h. It's all, so there's a limit here, there's a limit here. Both of them involve limits, in things going to infinity or going to 0. So what this is saying is basically you can interchange the order of those limits. This is huge. If you're in chemistry or engineering or physics, the idea of having limits of sums or sums of limits, or limits of derivatives or derivatives of, derivatives of sums or sums of derivatives, the fact that you can change this, well, it's not always true. It's true for power series. Now, I remember taking a statistical mechanics course, graduate level course in statistical mechanics at Cornell, and it was taught by a chemistry professor. It's a high-powered guy, and we were doing some calculation, and he got to some point where he said we can bring this derivative inside, or we can bring the limit inside or something. And I raised my hand and said, well, so why do you know we can do that? And he said, well, that's for the math people. The math people can explain why you can do that. And at that point I thought, well, this is silly. Well, really what I need to study here is the math, because the reason this chemistry works is apparently the math. So you want to learn this stuff, because otherwise you're just some drone. Well, that dude was not a drone, believe me. So here we go. But we can do this derivative. Remember that the derivative of this is a constant multiple, so that just slips through. And this is just something we can use the chain rule for. So this is the sum as n goes from 0 to infinity of Cn, and I'd have n times x minus a to the n minus 1. There we go. And there's also an analogous theorem for integrals. Suppose I have a power series. And I put that whole thing inside of an integral symbol. So take the sum first and then do the integral. The theorem says you can actually do the integral first and then do the sum. So again, we're just changing, because again, the integral involves a limit. The sum, the series involves a limit. So we're just interchanging order of limits. And then we can use the power series for antiderivatives here. And this is going to be the sum as n goes from 0 to infinity. The Cn is going to remain. And we're going to have x minus a to the n plus 1 over n plus 1. And then there's going to be, of course, with integration, there's going to be a plus c on the outside. So let me do an example where I use this. So this is example 3. Find the power series representation for this function. X over 1 plus 4x squared. Now, before we go any farther, what's the domain of, Ian, I'm picking on you today because you're wearing a hat. No, because you've gotten so good at this. What's the domain of this function? No, the square's on the outside. Andrew, you're in my line of sight, so maybe you can tell me, what's the domain of this function? What are the bad x values?
It starts at 1, it goes down.
Well, think about this. What would cause the denominator to be 0?
Negative 1/4.
Yeah, so the domain is, of the original function, is all x that are not equal to negative 1/4. Just that one bad x value. Okay, so there's that. And then let's do preliminary work. What is the derivative of 1 over 1 plus 4x? Well, you use the chain rule. You get minus 1 over 1 plus 4x squared, and then you have to take the derivative of what's inside. So you'd have minus 4 times 1 over 1 plus 4x, that thing squared. Well, look, we don't quite have that, but that means that if I have just 1 over 1 plus 4x squared, that thing by itself, that's going to be 1/4 of the derivative of 1 over 1 plus 4x. So that's just some preliminary, that's going to be minus 1/4 times that derivative. So that's just some preliminary work. Okay, so now we're going to do what we did before. We're going to rewrite the function f of x. So f of x equals x over 1 plus 4x quantity squared. And so that's x times 1 over 1 plus 4x quantity squared. And that's x times a minus 1/4 times the derivative of 1 over 1 plus 4x. So we're getting closer and closer to having a star in there. So that's x times minus 1/4 times the derivative of 1 over 1 minus a minus 4x. There we go. There's our star. We've got one of our star things going on. 1 over 1 minus blah. And so I can replace that with the series. X times minus 1/4. I still have the derivative symbol sitting here, but this is the sum as n goes from 0 to infinity of minus 4x to the n. Now this is only valid for x in this interval, minus 1/4 to 1/4, because the radius of convergence is 1/4. Okay, but that's okay. We're kind of resigned to that fact that you get this cool power series, but it's not good for all x's. But we're not done. I've got a derivative on the outside of a series by that theorem. This is x times minus 1/4 times the sum of the derivative. Move the derivative inside. Oh, you know what I should do? I should not use the theorem yet. I should clean this up first. This is x times minus 1/4. I still have the derivative symbol. And then I have the sum, and I have minus 1 to the n, 4 to the n, x to the n. There we go. Now I'm ready to bring the derivative symbol in. So x times minus 1/4, and I can bring the derivative symbol inside the summation symbol. Now recognize the only thing that gets snagged by that derivative symbol is the x, the power function. The other things are just constants. So they just come right past the derivative symbol. Minus 1 to the n, 4 to the n, and this is going to be nx to the n minus 1. Isn't that cool? We're getting closer. So now I want to make this an honest to goodness power function, so I want to bring this x in. That's going to make that x to the n. I want to bring this inside. That's going to affect the 4, and I'm going to bring the minus 1 inside as well. So this is going to be the sum of minus 1 to the n plus 1, because I brought in an extra factor of minus 1, and then 4 to the n minus 1, because I brought in a factor of 4 in the denominator, and then n, and then times x to the n. Isn't that cool? So there's my power series. There's my coefficient, and there's my power function. And this is valid for x in that interval. All right, we should do our quiz.